afternoon. This is Rice University's What's New program, and I'm your host for the series, Thad Marsh of the Rice English faculty. Today we pay a visit to the Rice campus to see a very complex electronic installation, the Rice Digital Computer. I shall be talking with Dr. Martin Graham, who showed us around the first stages of the computer project on this program 2 years ago. We shall also meet several other members of the Rice faculty who are especially interested in the computer, but I shall introduce them when we get to the computer laboratory. The wide usefulness of the research represented by this complicated machine, the computer, has been recognized by support by the Atomic Energy Commission as well as by industry. So I hope you will join us now in a visit to the completed computer.
And now, KTRK Television takes great pleasure in presenting the 8th in the Rice University series, What's New? Your host for the series, Thad Marsh, with today's guest, Dr. Martin Graham.
Marty, we are here now back at the Rice Computer Project, and
welcome back to the Rice Computer Project.
Thank you. We remind our audience that we visited the Rice Computer Project 2 years ago when it was in a state of incompletion, I guess you'd say, wouldn't you?
Yes.
In fact, I think our camera might be able to get in at this point and find out exactly where we were 2 years ago.
Yes,
when we left.
Recall, this is how our program ended that time.
I think it was.
The main difference is this tube now has information stored on it, and 2 years ago we were just beginning to test this section of the machine.
Well, we are calling the program the completed computer, though I suppose that's somewhat of a misnomer in our research project, isn't it?
Yes, we feel that this computer will never be completed because the computer was constructed at Rice for two purposes. One, to provide a tool for people to use in their scientific calculations, and also as a research device for people in building computers.
Yes, and that last one is best served by making alterations continually, isn't it?
Yes, and it's the sort of research where you need a full computer before you can start doing any work on it.
Yes, I don't think we probably have time to talk about it today, but I have heard you or one of your staff say that you can use the computer to design a computer. Is that true?
Not completely, but there are certain sections of the design that turn out to be rather tedious. Sometimes you're doing a section where you don't know exactly what values would be best and most reliable, and it's rather tedious to try all the different combinations. So you can decide how you would do the calculation and have the computer do the tedious part for you.
Very good. Well, I wonder if you would remind our audience of just what this particular section is, very briefly.
Yes, this was the first memory bank of the computer. It stores 8,000 words of either information, data, or instructions.
In each one of the tubes?
Yes, in each of the tubes we have 8,000 discrete dots. Each one can store a 0 or a 1 in the binary computer. And there are a total of 63 tubes, so each word or piece of information will actually in the computer consists of the first 56 tubes.
I see.
So it's a 56-bit word, and this is equivalent to about 16 decimal digits of accuracy. And this is one of the unusual things, the large word length and the great accuracy of this machine.
I see. I wonder if you could tell us a little bit now about the about what is completed that wasn't 2 years ago. Perhaps we could pay a visit to the arithmetic section.
Well, I shouldn't say that the computer is really not completed at all. It is completed to the extent where it is able to do computation. This section was the one that we sat in front of last time, and it's the arithmetic section. The string of racks is the one that actually takes the numbers from the memory and does such operations as adding two numbers, subtracting them, multiplying, dividing, and also operations such as comparing two numbers, seeing which is larger and which is smaller.
I see.
And then the next section, which didn't exist 2 years ago at all, is, again, a row of 10 racks, and this row is called the control section. It controls what happens to the numbers in the memory and in the arithmetic unit, whether they should be added or subtracted, and sometimes on the basis of what the numbers are, decides it should then proceed one path of calculation or another path.
I see. All right, well, let's join some of your associates here to see the control panel, the rest of the computer, and find out a little bit about what actually goes on here. Well, first, let me introduce some of your associates. Professor John Kilpatrick, Dr. Kilpatrick, Professor of Chemistry, Dr. Zevi Salzberg, Associate Professor of Chemistry, Mr. John Iliff, Senior Research Associate in the Computer Project. I heard a little bit going on here, John, as we were coming up. What sort of operation were you doing?
Oh, we were letting the machine solve a little puzzle.
What kind of puzzle do you have?
Puzzle consists of 12 pieces, in this case made of plastic. Each piece is made of exactly 5 unit squares, and no two pieces are the same, and the game is to fit the pieces back into this box once it's been dumped out.
I see.
The more general game is to fit this set of 12 particular pieces into an area of 60 square units, 5 and 12, that's any shape you like. We've coded up a general routine for the machine which will accept a typewriter drawing of the shape that we like the pieces fitted into.
And is that shape the same shape as this box?
Well, the one we were trying just now is exactly the same shape as this box. 6 units wide, 10 units high.
I see.
Would you like to see it run?
Yes, I would very much.
Here's the typewriter copy of the statement of the puzzle. We merely type in an X to represent each unit square. This figure has 6 X's horizontally and 10 rows vertically, and is terminated with a period. There's a second game down underneath it in which we left out the cross piece and put it over to one side in order to force the machine to find all solutions which have the cross in a particular place.
In that one particular position, yes. I see. Well, could you show us just how the machine is able to deal with a puzzle that begins with plastic pieces?
Well, we describe the pieces numerically, and we have a routine which handles this numerical data. And when it finds a solution, then it transcribes this numerical data back into the form of a line drawing on the fast printer, which is right behind me.
Yes, well, while you're putting that in, I might just go over here and show the machine that is the fast printer. This is the machine over here. And now you're putting in instructions to the computer?
The code for the problem is now loading into the reader, and one can see the pink tape squirting through the reader. The problem is now in the machine. And here's the paper tape, which has the description of the puzzle. The typewriter, which I typed out the drawing I showed you a moment ago, simultaneously punches the information into paper tape.
Oh, I see.
I'll put the paper tape in.
And that tape is read by the light beam that goes underneath. Is that right?
It's a photoelectric system. The first thing that the routine does is to make a line drawing of the statement of the puzzle.
I see.
And since I've run this before, I know that in something like 30 seconds, it'll find its first solution. Simultaneously, it will print out the total number of pieces that it's put on the playing board in finding this solution.
I see, and it's working on it right now.
Yes. If we look at the lights over here,
all right,
control console, we see them flashing off, and thousands of orders a second are going through. We have a solution. And there will be 3 more solutions that will come in rapid-fire order after this. They occur in a group of 4, which differ from each other by commuting a couple of adjacent pieces.
I see. What about the time lapse there, John? What is it that takes this much time for the machine to get to its first solution?
Oh, the machine is systematically trying to put the pieces on the playing board in all possible ways, and it made 747 plays in finding the first solution.
I see, and it was attempting with electronic equivalents of the pieces on the board to put them in the right place.
Yes, it has. The memory of the machine contains a numerical description of the shape of these pieces, which I could change around and change this game into another game if I liked.
I see. Well, what are? Can you show us here what the solutions look like?
All right. Here's the typical set of solutions.
Yes, the puzzle has altered each time the printer goes into operation.
That's right. We could set the machine in order to display how the puzzle is completed play by play if we wanted to, doing working in that mode, it would take an extremely long time to find a complete solution.
I see. But I see here, tried 779 times in order to get these solutions. Now it seems to be giving us another solution.
Yes, there's another solution. Let's have a quick look at it.
Well, now, in that particular lapse of time, the machine seems to have tried another 2,200 times before it got this one solution.
Yes, it plays at something like 100,000 moves an hour.
I see. Well, I don't quite see. Maybe Zevi can answer this question. What is the significance of your working with this particular kind of puzzle, Zev?
Well, aside from the intrinsic interest in the puzzle, I have a very special interest in this particular puzzle.
What is that?
Well, I just want to find out how many solutions there are to the puzzle.
Well, now, have you found out that answer?
No, not yet. In fact, I hope John will supply it to me in a day or so.
Oh, really?
Because several years ago, I got interested in a rather important and interesting scientific problem having to do with the properties of crystalline lattices.
That is an actual physical structure?
Yes, an actual physical crystalline lattice. The problem that goes under the technical name of an order-disorder problem in crystalline solids. And one of the aspects that we're interested in involves this interesting problem. I happen to have a reprint here of the paper in which the problem was proposed.
I'll show that while you're...
If you look at the figures in the central part of that page, you notice they have a certain similarity to our puzzle pieces.
Yes, they're exactly the same shape.
Yes, and they're called correlation figures in the lattice. The contributions that we're interested in involve counting the number of ways in which those correlation figures can be fitted into the lattice.
I see.
And you see, this is the same way as counting the number of ways we can fit these plastic pieces into the puzzle.
Well, isn't it a rather odd coincidence that a puzzle that begins with bits of plastic in a box turns out to have scientific relevance?
Well, at first it may seem strange, but this is actually a very common occurrence. As a matter of fact, almost any scientific problem you want to propose has certain mathematical aspects which you can also find in the theory of games or in the solution of certain puzzles. As a matter of fact, this is often one of the more convenient methods of solving a scientific problem, is to take advantage of the analogy between the puzzle and the scientific problem, and for the purpose of working the computer, you often make use of solving the puzzle.
I see.
And in this way, getting the answer to the scientific problem.
Well, that's exactly the way it's happened in this case for you, isn't it?
Yes.
With the pentomino puzzle that we've just seen the machine working on.
Yes, it's still working on it, and I hope it'll get the answer that I'm interested in. This type of problem, or this type of method is so common, it's called the Monte Carlo method.
And well, I suppose that indicates, doesn't it, that the games that you're particularly interested in are gambling-type games?
Yes, more often than not we use gambling games. This type of game is a little exception, but nevertheless we're going to find it very useful once we get the solution.
I see.
The computer here is particularly suitable for solving this type of problem too, and that's why we're making use of this method.
Yes, Marty, I'd like to ask you about that particular question. What are some of the unique features of this computer that make it really quite different from other large computers? I assume there are some that are comparable in size to this one, but we regard this one as somewhat unique.
Well, I already mentioned one of the unique features, and that is the length of the word that gives it this great accuracy, which is particularly useful for scientific problems. Another unique feature is just that the computer exists at a university campus and was built at this campus. You see, there are many university campuses that have commercial machines, and they serve the purpose of a tool for the users, but they are not readily changeable by the engineering people, so that it fulfills one research aspect, but not the field of how you improve computers. Now, this computer not only has a long word, but has a great deal of flexibility, which makes it easy to use, easy to do the sort of things that John Iliff wants to do with it, and easy to do the things that the chemistry and physics people are interested in doing.
I see. John Iliff, what about your particular contribution to this? It's in the field of programming. Does this have something to do with the language that the machine understands? And can you tell us something about that language?
Well, my main interest is in programming and giving instructions to the machine telling it what you want it to do and ensuring that it will do it and give you enough information to give you the solution to your problem. Here we're sitting at the control panel of the machine, and I can just stop the calculation by putting that switch up.
It was still working at that point on the pentagonal puzzle.
Yes, when I put it down, it goes again. See? Now, you've just seen the memory unit on the machine, and you understand that numbers are stored in there in the forms of patterns on those tubes.
Yes.
At the same time, we can store instructions in the form of patterns on the tubes.
Those would be in forms of numbers also, wouldn't they?
They look just the same as numbers, but instead of performing additions and subtractions on them, these are used to control the sequencing of operations on the other numbers in the memory. Now here I've got a display of a particular instruction in the machine. And here I've got a display of the address in the memory where that instruction came from.
I see.
And every time I press this button, it changes the instruction and executes it and proceeds through the code like that. This is the language in which the machine speaks. And I can show you a very simple thing, which is to type into this instruction register an order which will simply say type out on this typewriter the contents of a certain memory location.
All right.
And when I press this button to start it again, it should type that number out.
I see.
Actually, the way I've got it set up, it'll carry on typing it out.
And this is actually reading something from the memory of the whole computer then, isn't it?
Yeah. This is an unusual feature of the machine, that we can set it into a state where it will repeat a given order indefinitely until a certain condition arises.
I see.
It's a very useful programming device.
I wonder, John, if you could give me an example of a simple sequence of orders that would give our audience an idea of what kind of operation the machine goes through in a simple sequence.
Well, I have on hand a simple routine which will accept a large decimal number typed out on the flexowriter and stored in the form of a punch paper tape. We'll completely factor this number into all of its prime factors, quote out the number of times that each factor occurs, and perform the whole operation very rapidly. As a matter of fact, it'll work just as well on a long sequence of extremely large numbers. This particular routine is designed to accept numbers up to as large as 100 million. We could have designed it to accept numbers as large as we like, and of course it would run correspondingly slower.
Yes. You have a...
Suppose I load the routine in the machine, we give it a try, and you can propose us a number that we'd like to factor.
All right. I happen to have here, in my pocket somewhere, a dollar bill that we have already used the serial number from to give the machine its instructions. The serial number on the dollar bill is 421-73319. Now, you have a tape available there where we might show the typewriter while we're putting this in. We might show the typewriter that Zevi has moved over to, on which the paper tape is punched with the serial number of this dollar bill.
The routine's actually ready to accept it right now.
Well, all right.
Go ahead and have it type one.
Would you put this number in? 421-73319. And then you could show us the tape that is identical with the one that we're going to put into the machine just now.
Care to turn it in?
Was the machine doing anything, John, during the time that Zev was punching out this tape on the typewriter?
Well, for the first few seconds, yes. The tape containing the problem routine was loaded in, and then the machine calculated for around 15 seconds, accumulating a table of all the prime numbers between 2 and up to 10,000.
I see.
And then it stopped and waited for a problem to be proposed to it.
All right, well, here's the problem. Will you propose it?
All right. This is the dollar bill serial number.
We've already got the answer to that
Suppose
question?
we give it a whole series of numbers and see just how fast it goes.
Are these also dollar bill serial numbers?
They happen to be the bills that are in my pocket. Some of them go relatively fast, some of them are a little slow. Depends on how large the factors are.
I see.
Every time it prints, it's completed a factorization. Some half a dozen numbers on the list. Now here's our list.
All right.
It says here that your serial number, which was 42173319, factored into 3 one times, 53 one times, and 265,241, a prime number, which won't decompose.
I see.
And some of the other typical ones down here were ones like 89,867,392, factored into 2 7 times, 139, and 5,051.
And each one of those numbers that it puts out is prime. We can perhaps get a view of this kind of answer that the machine puts out. Now I notice at one point on this paper the number 46,365,071, which was one of your serial numbers, turns out to have been a prime number, and the machine prints out simply
That's right.
prime.
And
at that point.
It took it about 4 or 5 seconds to find this information.
I see.
You had to try all the prime divisors, less than 10,000.
I see.
Into this number.
Uh-huh. John, I wonder if you could tell us, is there any other language besides the one that you've already described to us that the computer understands?
Well, yes. You might say, well, communicating with a machine in terms of numbers is going to be both time-consuming and difficult for you because we make so often trivial mistakes with numbers which mean a lot to the machine.
Yes.
So for a long time, people have been able to say, I will identify my numbers by names, such as X, Y, and Z, like we do in algebra, and I will identify the operations I want to perform by means of words like add and subtract and multiply. And with this understanding, you can feed into the machine a program which has the equivalents for all these codes where necessary, and it will make up equivalents where it needs them for the storage of numbers and so on.
I see.
And you can feed in a program in this type of form, which is the so-called symbolic code, which the machine will read and translate into its own numerical code.
I see.
Not only that, but it prints out the equivalents that it's assigned to certain symbols, and if it finds what it thinks is a mistake, it will also print out error in so-and-so, saying it thinks you've made a mistake in a certain order.
Does it ever say, call you names?
Well, it could, but it doesn't. It's very polite for the machine. Now, the program is in the machine now, and this is the
already stored in the memory.
This is a symbolic tape with that code on it.
I see.
And it is read just like the numerical tapes, but it's processed in a rather different way. And it'll print out what it's doing in the process. At one point, I think it has indicated that an error occurred, and by referring to my original text, I can decide whether that's my fault or something deliberate.
Yes.
And now it punches out the final program in numerical form.
And this then is something that you can use again in the machine as the new language of the machine. Am I right in thinking that you yourself have devised this this particular language for the machine?
Beyond that, one can go to things like normal algebraic notation and hope to encode that.
I see. Well, before we run entirely out of time here, I'd like to get these gentlemen to tell our audience a little bit about the particular uses of the computer. Excuse me. What I would like to know is, you two being chemists, I wonder if if you could give our audience some idea of the particular kind of problems that the machine can solve that are of particular use to you in your own research.
Well, we're primarily interested in theoretical chemistry. We have a feeling that, in principle, many of the problems of chemistry have been solved, or at least could be calculated from the fundamental principles of physics. However, we need computers of this sort in order to actually carry out these calculations, and then, of course, we will apply them to actual chemical systems.
John, do you have a particular problem, for example, that you're interested in solving that this computer will be specially fitted to do?
Yes, I'm very much interested in solving some problems in quantum mechanics. This has to do with the calculation of the properties of chemical substances from pure theory. Some of the very simplest molecules have not been handled accurately by quantum mechanics, and we believe that the theory is capable of predicting results which previously have only been measured in the laboratory.
I see.
And I'm working on the problem at the moment of the electronic binding potential of the hydrogen molecule, the simplest stable molecule one can handle.
Marty, I wonder if you could give us some indication of whether this machine is able to check its own solutions, or how is it possible to check the answers that you get from it?
Well, the problem comes up when the answer is suspected of being incorrect, or is obviously incorrect, whether it's these fellas' fault or my fault. And the first question that comes up is who's to blame? And actually, they've written programs that we know the answers to, or that the machine can calculate answers to. For example, we have test programs that will test the machine's operation. One simple program is one that checks the arithmetic. It does a division, and it does a multiplication, and it adds in the remainder, and then sees if it's the original number. And if it is, it tries another division.
I see.
And
well, so in effect, the machine is its own test
of the machine itself.
Yes.
But then
not of the designer.
Well, it tests whether the machine is operating properly. But now, if they put in a wrong instruction somewhere, or haven't formulated the problem correctly, they won't get the right answer. But that's their fault.
Yeah.
And what they do is this debugging procedure, and the machine is very is built so that it's relatively easy to debug by doing the orders one at a time or in a flexible manner.
I see. Well, thank you very much, Dr. Martin Graham, Dr. Zevi Salzberg, Dr. John Kilpatrick, and Mr. John Isla, for a very interesting visit to what we can call the completed computer, even though it is, being a research tool, constantly undergoing revision. Since this is our last program of the season, and incidentally also my last one for the Rice University series, I should like particularly at this time to pay a very well-deserved tribute to all those people, including Mr. Willard Walbridge at KTRK Television, the general manager who has very graciously made available this time to us, and the many other people. I think our audience would be amazed to find how many people are necessary to put together a program of this sort. We're particularly indebted for production to Wayne Thomas and to Nancy Dunn. We started out the year with Mr. Bill Wagner, who had been with us for many years and who has now gone on to greener pastures. The number of cameramen who have helped us through this year and through other seasons: Buddy Sauer, Don Newman, Perry Blankenship, Don Chapman, Harry Buck, Dean Johnson, Bill Odell, Bill Hall, Bill Gilbreth. They are excellent. Ace Stebbins in sound, Charlie Harrison, our announcer, Hal Buchanan on the floor, Paul Montague, our artist, Ralph Payne, an artist himself in lights, and Lila Gordon for publicity. It's been a great pleasure to me to work with these people. Thank you very much for being with us this season. Goodbye.
This has been the last of this year's series of Rice University programs. We invite you to join us next season for another stimulating series of programs presented by KTRK Television and Rice University.